All right, next up, Runqing will tell us about stateful differential operators for incremental computing. Take it away.
Thank you for the introduction, and thank you all for coming here. And my name is Runqing. I'm a PhD student from KIT. And today I'm going to present our recent work on incremental computing. And this is a joint work with my supervisor, Sebastian, at Erdweg. And so at first, I want to introduce what is incremental computing. And in a nutshell, it's just a technique that allows us to do efficiently updates the program's output by the program when the input changes, instead of doing full scratch recomputation. And usually, an incremental computation has two phases. And the first phase is called initialization, which is like a normal program takes an input and maps it to an output. And after that, whenever there is a change to the input, the incremental computation will apply a slightly different strategy to update the program's output by the program input changes. And this process will just repeat every time the input changes. And there has been a lot of research has shown that the incremental computing can be asymptotically faster than recomputation, and also usually the user can observe a 10x to a 10,000x speed up in practice. And I know that all of you here may come from different areas, and to draw interest, so I listed some our daily using tools at here, which somewhat supports incremental features. For example, the IDEs sometimes support incremental type checking or incremental program analysis tools. And databases support incremental queries. Even for SMT solvers, we can configure it to run incrementally to push or pop assertions instead of rerun the full checking. And so, as I said, incremental computation will apply a different strategy to update the program's output. So now I'm going to just introduce two primary approaches of incremental computing. And the first approach is called selective recomputation. And the representative of this line includes self-adjusting computation or incremental build systems. So the basic idea of this approach is to reuse the previous sub-computation results if the input to this sub-computation is not changed. And to show you what I mean, let's just quickly to consider an example of a string processing task. And as you can see, this is the diagram of this computation, which takes two strings as input. And on the bottom branch, we take a username Alice and apply the operator to uppercase to convert it into the capital case. And in the bottom branch, we take an email address and using to lowercase to normalize this email address to a lowercase. And finally, we take these two intermediate results together to get the final output. And now let's consider how the selective computing works if we just modify the second input by inserting a character G before the mail. And I have highlighted that here. This is a change to the input. This is a very small input change. And the incremental computation detects that, OK, since the first input is not changed, so we can directly reuse the result of to uppercase, which just take constant time. But since the input to lowercase is changed, so it has to do a full recomputation, which takes the time proportional to the second input size. And also, since the input to concat is also changed, we also have to perform another recomputation about concat to copy the first part into the final computation. So it also takes the time of big O of the size of the first input. Note that I just consider the string as a linked list in this talk, which is very common in functional programming languages. And so as we have seen it here, even we simply insert one character to the input, the cost of updating the output will take the time proportional to the original input size instead of the change size. So this naturally just leads us to the question, can we do a better job? So to find an answer, let's just shift our attention to the second interesting incremental computing approach, which is called differential updating, and the representative work in this line is incremental view maintenance, which is actually the core technique for incrementalizing database queries. And the basic idea of differential updating is to utilize the change values and to just build the incremental computation by chaining differential operators together, and the differential operators are the operators does not map values to values, but from value changes to value changes. And let's just go back to our original example to show how the differential updating works. So the first step to use the differential updating is to define what kind of changes can we apply to a value. And here I just define two types of general changes to a string, which is either an insertion at a given position or deleting some characters from a given position. And let's go back to our example. As we can see it here, in the top range, since we did not change it, so I just put an empty insertion at here. But for the second input change, it's just insert the character G at the index 7. And so as we can see it here, the efficiency of the differential updating approach really just depends on the efficiency of the differential operators. So now let's just investigate them case by case to see whether they can bring a better speed up. So let's start from a simple operator to uppercase, which just converts all of the characters in uppercase. And now we do a case analysis on the changes. So now let's think about what will be the output change if we change the input to uppercase by inserting a string. I think, so as you may have come up with that, it just for the effect of this input change just to insert the uppercase of this string to the output. So for deletion, it's even simpler because it's just index-based. It does not talk about the content. So we can just, and also to uppercase does not change the length of the list or something else. So it's just propagate this change. So from this example, we have already seen that the time complexity of delta to uppercase will just be proportional to the change size instead of the input size. So which means that we can get a asymptotic speed up if the input change size is smaller, very super smaller than the original input size. But now let's consider a more complicated example of the concatenation. And the concatenation just concatenate two strings together. And we think, and for simplicity, let's just think about what will happen if we change the second input by inserting a string. So the result is because the second input will be shifted by the length of the first input, so the output change of this insertion will also be shifted by the length of the size of the first input. And for deletion, it's similar. We also need to shift the effect by the length of the input. And I use the green color here as shown here. It's a kind of wasteful to recompute the length of S1 all the time. So, so why not we just remember this information when we use the delta concat operator, then which allow us to get the output change in constant time. So it's actually a asymptotic speedup I have observed here because usually the concatenation, if we do recomputation, it's linear. It has this time complexity is linear with the size of the input. Yeah, no, if we only consider second input change in this case. So if we come back, we can observe that if we use the differential updating approach to incrementalize this computation, we finally can get the time complexity will just be proportional to the change size instead of the input size. And so this is actually a more effective approach for incrementalizing some computations. But so far, actually, there are two limitations of this approach. And the first limitation is that before our work, only the efficient differential operators only exist in the domain of databases. For example, selection, union, join, aggregation. But also, actually now, as you have seen, the states actually play a very important role for efficient operators. But currently, there is no framework for designing and verifying such custom state differential operators. And this is just the starting point of our work. We want to develop a formal framework for developing and verifying differential operators that can utilize custom states. And we formalized this framework in Rocq because I have not shown that here, but actually these custom state operators are very error prone. So using Rocq can ensure that all of the operators derived from our framework must be correct. And okay, in the rest of this talk, I will just go into some details of our framework. And the first thing I want to introduce is change structure, which defines the algebra of changes. And I use the Rocq syntax that here we define it as a type class, takes two type parameters as the type parameters. T is the value type, del T is the change type, and the patch function takes a change and a value and gets an updated value. And VC is a binary relation which intuition is to specify what kind of changes are valid to a value, or what kind of changes will not cause default behavior of patch. For example, if we patch a natural number 1 with a -2, then it is default behavior. And usually these default behaviors are very dangerous when we start to do verification. So when we implement the change structure, we require the users to provide a valid condition relation. And let's just go to the change structure on strings, which we have seen part of it. These are the possible types of changes to a string, insertion or deletion. And now we can define the patch function for for updating the string by the changes. And finally, this is the new part where we specify a valid condition for the string changes. As we can see here, if that's an insertion change, we must require that the starting point of this insertion do not exceed the range of the string. And also, if we perform a deletion, we must ensure that all of the delete characters also stays in the string. And okay, and from these basic change structures, we also can build higher order change structures. For example, one very common change structure is for pair. Because sometimes the operators have more than one parameter. So we have to have some change structure on these multiple values to specify what kind of the change structure for the input of operators. So in our framework, the change structure for pair consists of 3 types of changes, either change the first value or the second value or both of them by utilizing 2 basic change structures, C1 and C2. And also, we have change structure for option values to, for example, turn a non-value to a sum value, and use a change to turn a sum value to another sum value, and also turn some value to a non-value. And also, we have the change structure for patching sequential changes, because sometimes it's hard to express a change using a single descriptor. So it's also very often used when designing differential operators. Okay, so far I have not talked about the correctness of differential operators, but it's actually very important because differential operators are basically want to use a smart way to update the programs, which has a lot of edge cases. And so let's just have a look at this diagram. We start from the 2 uppercase. First we have an initial computation that maps the input to the output. And then we also have there is an input change delta in, and we utilize the delta to uppercase and get the delta output. And so the question is, how do we know that the delta out is correct? And to do that, we can use a commutation diagram to show the correctness. And to check if delta output is correct, what we can do is to first use, if there's a change structure for the input type, we can get the updated input by using the patch function, and then apply the 2 uppercase to the updated result. And also, if we found that if we use the updated output to, if we use the output change to update the output, and the value is the same as do a recomputation from the updated input to the output. If the diagram commutes, then basically we can say that the delta to uppercase does a correct job. And so now we use the Rocq's module system to translate this diagram into the formal specification, and we start with stateless differential operators like to uppercase. And in this spec, we first require we need to provide two change structures for the input type for the output type to allow us to patch the values. And also, we need to provide a basic computation function and the stateless differential operator to map the input change to output change. And to prove this delta f is correct, we need to we have two axioms. The first axiom is that, okay, if the input change is valid, then the result of doing a recomputation using f is the same as updating the original result by the output change produced by delta f. This is also known as from scratch consistency in the terminology of incremental computation. And also, since our scenario is to connect a lot of these differential operators together, so we not only need to require that the input change is valid to the input, also we might connect this operator's output change to the next differential operator. So we also need the output change is still also valid to the original output value. And for string differential operators like string.length or to uppercase to lowercase, we all can model them as stateless differential operators. And now let's consider a harder case for stateful differential operators. It's a bit different because now we need to use states. And where the state come from? It's in our specification, it will come from the initialization. So if we were to use concat, and then in the first step, we first not only map the input to the output, but we also get the initial state, which we can use to efficiently react to the input change to get the output change. But more importantly, we also need to update state. And this process will just repeat and so on and so on. And so let's, after we know how the stateful differential operator works, let's have a look at the formal specification. And so the first part is still the same, the change structure for the input and output, and also the initial computation function. And the next part is more crucial. We need to provide a state type, and also init function that initializes the state from the input, and also a delta st function which will take an input change and the current state to get the update state. But now I want to hold on for a second, because if we observe the signature of the delta st, it might remind us about the signature of the patching function. So that means that we can perfectly using the change structures to quantify the behavior of delta st. So instead, we just require the user to provide a change structure between the state type and the input change type. And also, for verification, we must specify what is the correct state, which we just put a invariant here. I know in the first talk, there is more interesting ways to verify the internal state is correct, but here we just use a customized binary relation, which is very general. And also the next part is about the stateful operators and its correctness. So at here, the differential operator takes the input change and the state and the get output. And so the valid property says that it's the same as the valid for stateless, which I just neglected here. And the correct means if the input change is valid and the state is correct, then the output, then the from scratch consistency still holds. So this is not the end, because we now also need to make sure the state is always correct in the lifetime of this operator. So the init says that the initial state is correct, and the inf step says that if the current state is correct, then after updating the state, it's still correct with respect to the updated input. And to explore the expressibility of our framework, we did several case studies. The first one is we use our framework to model and verify a bunch of novel string differential operators which do not exist before. And for example, we model is empty as a stateful operator which takes the length of the string as a state, which allows us to find the output change in constant time. And also for index of and last index of, we use the original input value and output value as a state, which allows us to update the output in the time proportional to the input size in most cases. There is only one case where if you delete the occurrence of the thing you want to find, you have to do some recomputation. And in the second case study, we also start to use our framework to model existing differential operators in relational algebra domain. For example, we modeled an incremental aggregation algorithm as a stateful operator in our framework. This kind of incremental aggregation is used a lot in the incremental program analysis in this real-world projects. And this is also the first mechanization of this algorithm in Rocq. And we also have successfully modeled the database differential join operator as a stateful operator in our framework. This shows that our framework is capable of modeling existing complicated operators and also is able to model novel operators to push this differential updating approach to the general domains. And what we also did is to extract this Rocq code to executable the OCaml code and build several benchmarks to test their practical performance. For example, this is the first one, which it consists of 2 selection operator and 1 drawing operator, and finally we do a max aggregation, and we just randomly put in union changes or deeping changes to this computation to test its performance. And what we have said here, this is the benchmark result, and the y-axis is the execution time, and the x-axis is the input size, and the blue line is the recomputation execution time, and the orange line is for the incremental computation. So lower is better, and we can observe that the differential operators can bring asymptotic speed up. And also another benchmark is about stream processing, which consists of operators like to lowercase and to uppercase, and we also can observe a significant speed up at here. So to conclude it, we designed a formal framework for building efficient incremental computations, and which supports custom state operators. And in future work, we want to investigate how to share the state to save memory of the incremental computation, and also ultimately we want to develop a standard library of differential operators for common data types. Okay, thank you for your attention.
Okay, in the back. Do you want to go ahead? You've got the mic.
Oh, okay, sure, thanks. Thank you for the talk. I was wondering, so it seems like most of your differential functions are user-defined. Have you explored synthesizing differential functions from the original definition?
We did think about it, but one interesting thing about the differential operators is these states actually are not intermediate results of the original computation. For example, the length of is empty is not sometimes not directly computed in original computation, so it's still far away from automatically synthesizing efficient differential operators from our framework. Yeah, I think that's interesting.
Yeah, hi, back here. Lovely stuff. You mentioned that you implement all the relational stuff that existing IBM engines like differential data flow or DBSB do. How do you compare to them?
I think they apply in a more restrictive applications, For example, in the differential data flow, you require there is a partial order on the state, and also this actually poses some obstacles for using this differential approximation approach in a broad domain. So our method is actually more, in my opinion, it's more general.
That wasn't my question. My question was about how you compare on performance.
We did not compare the performance.
Okay. A sort of follow-up, I guess we can't look at the slide. We saw on that graph there were 3 lines. You only talked about 2 of them. One of them was the improved time performance, but it seemed like you were experiencing the exact same time-space trade-off that something like differential data flow or DBSP would have. Can you explain how you might achieve some of the sharing? You said that this was future work. Like differential data flow and DBSP can share arrangements. Yeah. What are you going to be able to share?
Yeah, for example, many differential operators use the input as the state. And suppose we connect 3 tail operators, list tail operators together. So obviously, they actually just use the same list, some part of the same list as their state. So for example, the first tail operator uses the tail of this list as the state, and the second tail operator will use the tail of the original input as state. So obviously, there are some opportunities for sharing the states.
Okay, thank you.
Yeah.
Okay, let's thank the speaker.
Okay, thank you.